We're just waiting one more minute to get started. Broken. Okay, hi everyone. I think we'll get started. Thank you very much for coming. My name is Zoe Johnson, and I'm very pleased to welcome you to the session. Today's event is going to feature 5 presentations, followed by a panel discussion. And since we have a very full schedule, I'm not going to take up any more time, and I'll just pass the floor right away to Dr. Brian Menounos. So Dr. Menounos is with the Geological Survey of Canada and is a full professor at the University of Northern British Columbia. And is a former Canada Research Chair in glacier change. He's an expert in climate and glaciers, including their past, present, and future. So Dr. Menounos is going to be talking to us today about how we assess glacier mass change. To you.
Thanks, Zoe, and thanks, James and the panel for organizing this. So I want to talk to you a little bit about how we measure mass change, specifically in Western Canada. And I'll just wait a little bit until the slide deck loads, but I'll give you a couple examples from Western Canada. There we go. Okay, we can, to save some time, let's skip to the next slide. Okay, so I've got to show a picture of my favorite glacier. This is Clean Glacier, and it drains the Heiltsuk ice field, which is about 1,200 square kilometers in central Coast Mountains of British Columbia. What's hard to take away from this beautiful image of this glacier is that this particular ice field loses on average about 1 gigaton of mass per year. In really bad years, it gets up to about 2 to 3 gigatons a year. Next slide. Okay, so most of the work that I've done is actually on glaciers in Western North America, but when we think about North America in general, Canada and Alaska contains about 36% of the global ice volume based on surface inversion models. And it's really a 2-part story. So part 1 is about sea level rise. So that's primarily the ice in Arctic Canada and Alaska. And then when we think about smaller glaciers in Western Canada, we're really talking about the thermal and water buffering that's provided by that melt during late summer. Next slide. Okay, I'm going to show some cartoons here. I think we've all seen these sorts of schematics, but here's a typical hydrograph for a glaciarized basin. And when we talk about glacier contribution, it's really that green component of the hydrograph there. And if we think about a glacier in disequilibrium with climate, so a warming climate, then we actually get what's called a dividend surplus excess. So if you hit the next slide there, that's the component that we're talking about. So when glaciers are in a bad state, they're undergoing wastage, that's the component that's being fed to the streams. And if you go to the next slide, you take away that slice. And so that's sort of thinking about what the future lies for some of these smaller glaciarized systems in Western Canada. Next slide. So approaches to measuring mass balance, we have a variety of different techniques. This is from my colleague Etienne, who's actually here in the audience today. So we have probably the longest and most the oldest histories are the in situ measurements. These are collected at a handful of sites throughout planet Earth, but they are quite limited in terms of spatial extent. And so we have a second method, which would be a geodetic, and so a volumetric change. The advantage there is a more regional coverage, but of course we have to convert that volume change to a density conversion. And for the large ice fields such as Arctic Canada and Alaska, we can actually use gravity anomalies. Next slide. This is probably the 12th time this graph has been shown at this two-day event, but I want to focus in on Western Canada to provide this example. So over the 23-year period, these glaciers have lost about 23% of their volume, so a tremendous amount. And I'm going to give you some examples for the last couple of years. So Glanbey used in situ measurements, it used laser altimetry, it also used radar altimetry. And in Western Canada, we also have geodetic methods that for the last couple of years using an aircraft, and I'll give you that example right now. Next slide, please. So for the last decade, we've actually had the opportunity of a great partnership with a nonprofit organization to conduct airborne surveys over some of the ice in Western Canada and the conterminous US. And so some of these sites we repeat about twice a year. Other areas we fly once a year. And so this gives us about 10 to 15% coverage for glaciers in Western Canada and the lower 48. Next slide. Okay, I think many of us have heard about how extreme 2023 was in terms of global loss. In particular for Western Canada, it was truly off the charts. So the image on the left here, this is a MODIS image showing smoke from wildfires, so our worst wildfire year, but it was also our warmest in many parts of Western Canada. And if we were to look at the elevation change, and if we could go back to that slide before that one, you'll see how dark those surfaces are. Oh, no, if you can go back one. Oh, there we go. Okay, so that's the surface of Yoho Peyto. So Peyto Glacier is in the north, so that's the one that John was talking about earlier today. This was at the end of summer, so almost like 2 to 3% retained snow. So it was, in addition to being warm and that thermal energy, we also had a tremendously dark surface, which would absorb more energy. And some sensitivity studies that we've done, Sean Marshall at Hague Glacier, shows that component, the darkening, represented about 20% of the, could explain 20% of the mass loss for these glaciers in the Rockies. Next slide. Okay, now you got to go one more. Thanks. Okay, so here's my final slide. So putting this all together, if we sort of think about the mass change expressed as a mass balance, so over the surface, we can see that from about 1965 and for the several years that we've been, that I'm reporting here in terms of laser altimetry, and then going forward, this is Matthias Huss's global evolution model, you can see that the surface mass balance increases. That's not surprising as temperature continues to warm. If we look at the mass change, so we take that thinning and we represent it over the area of the glacier, we see that we're perhaps at that point where that excess dividend is reached a maximum, and we're expecting to see, based on the simulations, a reduction in the total volume going into many of these headwater streams. And so this is work that continues with respect to the monitoring. It's only one of our techniques, and so Glanbey, of course, represented a whole variety of different techniques. And one thing we hope to do with our partners with Glanbey too is to use the rich laser altimetry that we get from the aircraft to look at some of the uncertainties that are based on either the in situ or the spaceborne observations. And I'll leave it there. Thanks.
Okay, thank you very much, Dr. Menounos. Next we have Dr. Anna Barros. She's a professor of civil and environmental engineering at the University of Illinois, and she specializes in the physics of the water cycle processes in mountainous regions and remote sensing of the environment. Dr. Barros has a PhD in civil and environmental engineering, and she'll be talking to us today about global snow observations from space, realizing the potential of SAR. Thanks for being here.
Well, thank you very much. And so we're going to look really at the seasonal snow part of the problem, and really focusing on the benefits and the uses of synthetic aperture radar. I put in there that this is a presentation of mine, but with input from the Snow Globe team. The Snow Globe team was a team that was put together to submit an Explorer proposal to NASA, and so a lot of the insights here are really a team effort. And so how do I do enter? Okay, here. And so I will start by looking at the changes in climatology of precipitation and of snow globally, and we can see increases in frequency, increases in magnitude everywhere. In the Great Lakes region in the US, a change in how long the snow stay on the ground, and even those lake snow effects are actually increasing. We see that the snowpack stays for much shorter periods of time. The other thing is when we look at climate projections, and I find this really interesting, is that these changes that are coming are a seesaw, an east-west seesaw over Asia and Eurasia, and really a north-south seesaw over North America. And so this is really interesting because it's related also to weather patterns, the storm track, and it really captures the potential implications at global scales of changes locally that have implications at global scales. Of course, even though, some of these projections say that we'll have fewer snowstorms, we're talking about much more intense snowstorms that will last shorter periods of time on the ground. And in fact, in the US, if you look at the number of blizzards over time, we see that they have been increasing at very, very steep rate over time. So we do have this picture. And then on the other side, we have the lack of snowfall at high elevations. If you've heard about all the drama with water resources in California, this is a typical case of what can happen in a mountain ski resort. But it's really, from a water resources point of view, the impact is on reservoirs, right? And how we see the water levels going down, and the implications it has for hydropower, for irrigation, and for actually also regional microclimate. So we talked about this morning about the implications and the costs of these snow events, of decreasing snow. A snow drought in California costs about $45 billion, or about $50 billion, and this was important for us to actually have in the analysis of our mission, because the cost cap of the mission was about $400 million, and so it's 1 in 100, sort of, or 1 in 1,000 sort of benefit in terms of getting this data and understanding processes. Another very important change that we have witnessed in North America, and actually my office was smelling like smoke from Canada last summer, and I'm fairly down in Illinois, are wildfires around the higher latitudes, and these really are just mapping changes in high latitude convection. And so what we see here are these implications of global changes that are local but are really happening across latitudes and impacting areas very far away. So in terms of the science needs, how we saw them in terms of putting this mission together, we were really interested in getting global observations of SWE. And that means snow water equivalent, and it means that we're not just interested in mapping snow cover, we're not also just interested in mapping snow depth, but we actually want to know how much water is there, and that is really snow mass. Then we really wanted these measurements at very high temporal frequency, and that's basically the inter-arrival time of storms in the mid-latitudes and in the north latitudes. And then, of course, capturing snowmelt patterns and intermittency, and really understand process scale. So we can take our models, like Crocus and ours, which is MSHM and so on, and really validate the models and understand how we can go from where we are now to improving better prediction. We have made use of Sentinel-1 C-band SAR. So C-band is not an ideal frequency to look at SWE, at snow water equivalent, because it actually just goes through the snowpack when it's dry. But what it does, it provides us really a good measure of what SAR can do for us, because you can get these super high resolution or hyper resolution data sets. And after carefully processing and looking at how these processes scale, we can find that independently of time of the year. So in this central plot here, we have the change in variance over that area on top in Grand Mesa in Colorado at the different times of the year. So you can look at those different colors as basically one hydrologic year, and so changes in the spatial variability or heterogeneity of the backscatter signal from the synthetic aperture radar. And as you can see, even though the variability changes with time, what we find is that at some scales, at about 100 to 250 meters, we actually reach a minimum variance, which is sort of a phenomenon that we see a lot in hydrology, right? We do have an ideal scale at which variance is minimum, and then it starts increasing again because of topography, because of radiation exposure, and so on. And so based on this, we really had really useful information about what would be the scale at which we wanted our synthetic aperture radar mission to function. However, in order to do what was prescribed to us as part of the decadal survey, which is a process of setting priorities for space missions in the US, we actually had to think about this. So we knew what was the temporal resolution that we wanted. We knew what was the spatial scale that would really give us the best bang for the buck here. And then we wanted to also look at the solution, right, that would give us most of the volume of snow mass in the world. And as you can see, it's really, roughly above 55 degrees that we have more than 50% of the global SWE across longitude in the Northern Hemisphere. Of course, we also have snow in the Southern Hemisphere. I don't want to minimize that, but it's not as significant in terms of comparison. Although one colleague at University of Chile was also part of our team. How do I go back to where I was? Sorry, because that was how did I miss that? Let's go to a slide so I can just talk a little bit about the measurement solution that we have, the one with the black line on top, that one. So our final architecture for the mission that was proposed, Snow Globe, was that of a constellation at two frequencies, X and Ku, using synthetic aperture radar at 250-meter resolution. That was our target, with a 5-day maximum revisit, and so covering more than 95% of the seasonal snow extent in the world, and with pretty high requirements in terms of SWE uncertainty. Now, the importance of having a constellation mission is that in order to have the high temporal revisit that we wanted, we really could not do that with just one single satellite. And as you can see from this graph here on the right, what we're showing there is the percentage of mass seasonal snow extent that is covered by different pairs of satellites. So our design consisted of having a pair of satellites, one at X and one at Ku band, and they would just revisit every 3 days or it really depends on where you are. As you can see on the left, the darker blue color in the northern latitudes, the revisit time is much more frequent. As we approach the lower latitudes, the revisit time is longer. But in order to get really a 95% or so of the global mass extent, we needed about 5 or 6 pairs of satellites. And so that was the overall concept of this mission. One important thing for these missions, a mission like this had already been proposed, not like this, not a constellation, very different, but still the concept of measuring using synthetic aperture radar to actually get at SWE had been proposed in Europe. It was called Core H2O in 2010 or so. But one of the limitations then was the difficulty in demonstrating that we could actually do retrievals. We actually were very fortunate because NASA had a snow field campaign, and we collected observations, and we were able to demonstrate that we could retrieve not only snow depth at very high spatial resolution, and actually perform very well compared with LiDAR, but also to obtain SWE. And I think I only have one more slide. And I'm happy to. It's probably not the last one, but I could stop here because I was going to talk about data assimilation and I already took too much time. So I'll stop. Thank you.
Thank you very much.
No, that was wonderful. Thank you very much, Dr. Barros. So up next, we have Dr. Francesca Pelliciotti. She is a professor at the Institute of Science and Technology, Austria, and she works on modeling glacier responses to a changing climate and the effect of high elevation water resources on water security. Yeah. She will be talking to us today about the Pamir-Karakoram anomaly.
Great. Thank you very much for inviting me here today. The title of my talk is the Pamir, the full long title is the Pamir-Karakoram anomaly. It's nearing its end, and what can observations and models tell us? And I'm going to present today some work that shows how crucial it is, I think, to combine models. Yes?
The people online can see your face if you stand there.
When should I be there? Sorry. Sit down. I cannot sit when I talk. This is an Italian thing, but I can try. I can try hard. Okay, great. So I'm going to show some work that we did that shows how crucial it is, in my opinion, to combine models. And I'm going to argue today that we need models that are as physically based as possible and ground observations from monitoring catchment in particular. And I'm going to focus on a key region. This is the Pamir region. It's a unique region for two main reasons. It's the only region with stable or growing glaciers. It has been named the Pamir-Karakoram anomaly. I'm sorry, I mixed the two. And this figure is work that Evan published some time ago from work that Fanny, Brun, and Couters did that shows altitudinally resolved mass balance from every single glacier in high mountain Asia. And you see very clearly it's all red. These are mass losses. On average, one glacier loses 1 meter of mass in 1 year, except for this region here, where there is some blue and most is yellow. These are stable glaciers. This region is unique for another region. This is work that Walter Imagel and Couters published in 2020 in Nature, in which they classified the water towers of the world based on an importance and vulnerability. And that region in the Pamir, if my mouse works, yes, the Pamir hosts and sustains some of the most important and vulnerable basins in terms of water resources. So this is a key region. I just would like to show you how a growing glacier looks like. When I saw that this is the Kizulsu glacier, you can see the lateral moraine, and the glacier is level with its lateral moraine. I've never seen something like this. I mean, in the Alps, we see glaciers that sit deep into their moraine because they've lost so much mass. I don't know, I think in the Andes it's the same. So this was quite striking to us when we went there the first time. But it was remote sensing that shows those anomalous patterns. And this incredible work that Etienne Berthier and Fanny and Ines, she's also here, did from remote sensing. And it's also remote sensing that is suggesting that that region might nearing a change in mass balance regime, so that we might start seeing a decline in glacial health. And this is a figure taken from the paper that Romain Hugonnet published in 2021 in Nature. And this is a zoom in, a very bad quality zoom in that region, because that was a global effort, of course, in which you see the 5 years changes in the region, and you see that it's getting red. These are thinning rates, and you can see thinning and not thickening. So the question we were trying to answer was, okay, is it really like this? Is it really, there are uncertainties in that remote sensing estimates, of course. So we were asking ourselves the question, is it really like this? And we started to do some work, and Achille was driving this work for his PhD, Achille Jouberton, to reconstruct the long-term glacier mass balances, energy and mass fluxes and runoff in the region, to understand whether there has been a shift in mass balance regimes, and if then determine what had caused those shifts. And for that, we focus on one experimental catchment, is the Kizulsu catchment, as you can see here in central Tajikistan. We went there for the first time in 2021, and we started installing a number of instruments, a number of AWSs, a pluviometer, sorry, an automatic weather station, sorry for that, a pluviometer, ablation stakes. We measured debris thickness and properties. We had string gauges, time-lapse cameras, and we've been going there every year. And that catchment is now part of INARCH, or the International Network for Alpine Research Catchment Hydrology. It was great, it was included in it. It was really a push for us to do things the best we could. We use a model, of course, we are a group of modelers. We use a very sophisticated, fully physically based land surface model that simulates all energy and mass fluxes. And when I say mass, it means water and carbon as well. So it solves the physics of energy mass exchange for ice, permafrost, snow, but also for vegetation and all the other components of a mountain catchment. And I'm going to go straight to the results and get back to the data later. And those results show, indeed, a decline in mass balance driven by a decline in snowfalls. So this figure shows from 2000 to 2022 mass balance. These are the black bars that you see here. And you can see very clearly a decline starting very clearly in 2018, possibly before. And that decline was driven. So in the top panel, you see seasonal snow, including the snow that is avalanched onto the glaciers. And on the bottom panel, you see ice melt, snow melt, sublimation, and evaporation. So you can see that increase, that more negative mass balance was driven by a decline in seasonal snow. And crucially, the decline in seasonal snow was really due to less precipitation and reduction in the total amount, not a precipitation phase change. The precipitation phase change, we see this happening globally in many, many regions, and is one of the main drivers of these very high mass losses in the Eastern Tibetan Plateau. The Eastern Tibetan Plateau is losing as some of the highest mass losses, and we and other people have been doing work that shows that the main driver is the change in phase for solid to liquid. In this case, it's not. In this case, the solid fraction remained the same, and this is because there is warming, there is a very positive anomaly I'm going to show in a minute. But the key point is that in that region, accumulation is mostly in winter, is still westerly dominated. So even a 1 or 2 degrees difference in temperature will not affect, not yet, the phase of the precipitation. So this is really a reduction in total mass. So this is the main result. Indeed, a snowfall was also the title of the paper. I think a snowfall decrease is going on that undermines glacier health. These are the same results in a slightly different way. You see the mass balance decline, so the more and more negative mass balance. This is precipitation, and the color code is the temperature anomaly. I hope you can see it. So there is clearly warming, but as I said already, that warming is not enough to trigger a precipitation phase, or a switch from snow to rain. And this is the runoff. What is happening to runoff is very interesting. Runoff has been declining, but the runoff deficit is smaller than the precipitation deficit because glaciers are still compensating in the region, but there is also on top an increase of evaporation. So as I was trying to explain yesterday, those systems are very complex, and one needs to take into account all the components. So now, why were data important? This was part of my title, isn't it? We use a large amount of ground and satellite data for two main things: to validate the model and to constrain the meteorological input forcing. I want to make here very clearly the point that being this a model that is fully physically based, it doesn't need calibration. We didn't calibrate the model, but the major source of uncertainty are the input data. So we use satellite data, MODIS, Landsat 8 and Sentinel-2 for snow cover. We use mass balance derived from remote sensing. We use also, and I mentioned them earlier already, a large amount of ground data. So we had a number of AWSs. We measure snow depth. We install ablation stakes. This is a bit the traditional measurements of monitoring catchment. We measure string gauge, debris thickness and properties, because there is quite a bit of debris in the catchment. But I want to focus on one key observation, or one key source of uncertainty, in fact, which is precipitation. When we arrived in 2021, we installed an accurate pluviometer. John then told us, oh, you didn't have wind chills, so we immediately put the wind chills because we didn't want to incur John's. So anyhow, sorry for that. Anyhow, we put a wind chill then. And these are the glaciers. So this is the Kitsulsu Glacier there. So this is an hour from the glacier and very close to camp. But we also, this was a serendipitous thing, I think a really clever idea from Achille. In fact, we also decided to use the lakes that are in the region. These are lakes that freeze during winter as gigantic pluviometers. And we were inspired, and I want to acknowledge this, by work that Hamish Pritchard had done to show that one can use pressure level changes of frozen lakes as a gigantic pluviometer, as I said. And it was a clever, very clever method. We use it. And indeed, it's also a very easy, this is Tom, they went, put the transducers, I was not there when they did it, put the transducers, and you can recover the transducers the next season when the lake is unfreezes or later on. We had that for 2 years. And this is the key result now. So, well, the key result of that comparison. So the precipitation measure at the pluviometer, which is this dashed line here, was more than a half the one that the lake was measuring. And what we did then, we corrected that. We tried, this can be a debate. We trust in more the lakes. We can discuss this. But we corrected the pluvio record. We had those 2 years of observations, of the 2 independent observations. We corrected the pluvio data. We used that pluvio data then to downscale with quantile mapping and bias correct ERA 5 length to 100 meters. And this is the input that then we use to force our model. And the point I want to make is that it was enough to correct for those 2 years. So these are the 2 years for which we had the data, we corrected the pluvio, we downscale and bias corrected ERA, and then we use it to force the model for the 20 years. And this is an example of the reconstruction for the entire catchment of the snow depth. And you can see very clear the snow poor years and these negative anomalies, as I say, snow poor years. This is the forcing that we obtained then to drive our model and obtain those results that I show that indicate a decline, so a shift towards negative mass balance. So I'm going to finish here with a perspective. First of all, the science, I think these are very nice results. There is an inflection in mass balance regime. We see a shift towards negative mass balance due to a reduced amount of precipitation. Again, it's not a phase change in that region, not yet. There is a decrease in runoff, but that runoff deficit is still less than the precipitation deficit. Glaciers still compensate, is very important. But as I said, we also see an increase in evaporation, which also, so there is an offset of an offset, so to say. Now, in terms of data, then, this was the scientific result. This is also science, of course, but I think we do need those experimental catchment to constrain models. And when we have physically based models, we can really have also a few years of data will be enough, as I hope I've shown today. Now I have a few questions for later for the panel or for this audience. How do we choose those catchments? This is a question I'm asking myself since I started working in this field 20 years ago. The first point, often we are opportunistic, right? There is accessibility, local people have knowledge of the sites. For Kinsulsu, we talk a bit to Martin Earlsley, we really took a Google map and decided like that, I have to say, very, very frankly. And the other point, and the other key question we are asking, and the reviewers are asking too, is how is represented, the review of that paper, how representative is that area and catchment of the larger areas. We are doing work now to expand those findings to a larger region and possibly the entire Pamir, but really how representative can be a representative INARCH monitoring catchment? What it needs to be representative so that the results we obtain there are robust. And I think this is the last question, and I think this is the easier compared to the previous two. How do we make sure the measurements across those catchments are consistent? And with this, I thank you very much for your attention.
Okay, thank you very much. So up next, we have Dr. Ignacio Lopez. He's a geographer and researcher of the Pyrenean Institute of Ecology, working in mountain hydrology, mostly in the Pyrenees, but also with regular research in the Andes and Arctic zones. He's the co-chair of the International Network for Alpine Research Catchment Hydrology Network, INARCH, and he'll be talking to us today about how INARCH is an example of international collaborative effort to observe changes in high mountain hydrology. Thanks.
Okay, thank you. Yes, as you say, I am the co-chair of the INARCH initiative network, together with John Pomeroy and James McPhee, and the always support of Chris De Beer. And when we speak about alpine catchments, we refer to highly monitored sites that permits in relatively small areas to have a very good idea of the connection between climate, the cryosphere, and the hydrological response of those sites. Installing these catchments and maintaining in the long term requires a lot of effort, work and money, but I think that still is very necessary in these days. Please, next. Because despite that now, we have computational resources to run models of glaciers, snow, hydrology for very large regions, even globally, or the remote sensing products. We have seen that they are providing very, very nice information. We still need to have that ground truth in order to validate all these models and products, sometimes to calibrate the models, and what is more important, to really understand the processes that permits to improve our representation of the mass and energy balance of the snow and the ice, and how all this melt is routed to the river streams. We think that this is the only way to improve our projections on how climate change will impact on mountain areas. Next, please. Also, why to work in a network? One of the first things that we saw many years ago is that climate change in different parts is affecting very differently to the cryospheric elements. For instance, there are some graphs for the transect that was made from the Yukon to the Idaho to see how the same levels of warming are leading to very different changes in snow water equivalent. And then when we replicated this analysis to many mountains of the world, we can see, for instance, how 1 single degree of warming is not affecting mostly the accumulation of snow, but in other places maybe reducing even at 30 or 40% of this. So when we are working alone in one catchment, we are losing this reference about what is happening in other places. And next, please. Also, nowadays, we have a lot of instruments, from the very simple ones as tubes to measure the snow water equivalent to very sophisticated ones. Also, a lot of tools for simulation and assimilation that definitively, when we share the knowledge and the experiences on using them, we are saving a lot of time and we are optimizing a lot their application. And also, and for me very important, the collaborative science is not only better and obtain much better results, but we have much more fun. I think it's much better than working alone in your single place. Please, next. So I think many of these ideas we discussed with John Pomeroy years ago, and we decided with a group of, let's say, of scientists and friends at the same time to apply for a project to IWGP, to the hydrological panel, in order to measure and understand better the different processes that are affecting to mountain areas, to be able to improve their prediction as coupled systems and diagnose their sensitivities to climate change, and also to provide some ideas on how to manage better these areas. Also, with the idea of all these results to be a contribution to the UNESCO Intergovernmental Hydrological Program. Next, please. So we started in 2015, the first phase from 2015 to 2020 with the goals that I presented just before. And then in 2021, we started the second phase with more refined questions and activities that they are now underway. INARCH is also contributing to the UNESCO Church in mountain water sustainability, and also has contributed, as we are here, in the International Year of Glaciers, and definitively we want to be involved in the things that will happen in the Decade for Action for Cryospheric Sciences. Currently, well, the numbers are changing every day, but let's say that we are about 60 scientists working in 38 experimental catchments, 18 countries and 6 continents. Please, next. This is a more detail of the distribution of the INARCH catchments that I think is a quite impressive distribution across the world. One of the main things we have done since we started in 2015 is to organize annual workshops that have been only interrupted during the 2 years because of the travel restrictions of COVID. I think next, and next, yeah, it's fine. Well, you can go backwards or stay there. No, and simply to say that these conferences, workshops, they are between 35, 50 people, and we have had always a lot of fun there, but I can say by myself that I learned a lot, and I knew wonderful people, starting very nice collaborations that I think many of us has progressed as scientists in the frame of these workshops and initiative. And next, please. Also, we work actively organizing conference sessions. For instance, this year we are organizing sessions in the AGU, in the International Mountain Conference, and planning for the AGU next year, as we do regularly. And next. And also contributing, creating special issues for journals. I think is very remarkable, the special issue for Earth System Science Data. That is a special issue open since 2017 and still open. And we have gathered tens of datasets from different experimental catchments, and we are still open to receive more. And also the special issue that we have now open for hydrological processes, basically dealing with the main research questions that INARCH has from the very beginning. And just to finish, one of the interesting things we are doing in this second phase of INARCH is the common observing period of experiment, the COPE, with the idea to gather in the same archive datasets from 2022 to 2024, trying to obtain high-quality measurements, and at the beginning of this experiment to try to ensure that all sensors are working, that this is relevant because this was just after COVID, and for many experimental catchments was difficult to maintain the sensors working, so we wanted to push to put everything fine, also to share common remote sensing products to be used in all the catchments, and to force a little to have supplementary information like UAV acquisitions in order to run high-resolution models to make comparison, etc. So now we are collecting this data, trying to start to work very soon on these datasets. And I think you can go directly for my thank you, and I'm waiting for your questions later. Thanks.
Okay, thank you very much. So our last presentation before we go to the panel is going to be from Diraj Pradhananga, who's joining us remotely from Nepal. Dr. Pradhananga is an associate professor at Tribhuvan University in Nepal, a UNESCO chairholder in mountain water sustainability, and the president of Small Earth Nepal, a community organization that promotes sustainable lifestyles. He holds a PhD in glacier hydrology, and he's going to talk to us today about improving water resource estimations and risk assessments in the Himalayas. Thanks.
Thank you, James and Joe, for including me. It's great to be among, all very great glaciologists. While waiting for the slides.
Sorry, Diraj. We're just getting the technician. We're dealing with this sound issue. So just hold on for one moment.
Sure.
Does anybody have a question in the meantime that we could perhaps quickly address? Or comments or reactions from the other panelists?
Yes, sometimes. We don't prescribe measurements. We bring in sites that tend to already exist, but we strongly encourage soil moisture measurements. And then in some areas, we have permafrost measurements as well and groundwater observation wells. So, and that really adds tremendous value to the surface observations. So, but because the ground usually is seasonally frozen, we want to make sure we have both liquid volumetric water content and soil temperature along with both, so you can get the freezing characteristic curves of the soils.
Okay, Daraj, would you mind trying again?
Here. Am I audible now? Is it working? Hello. What
I'm
about
gonna ask
Jacob? Can you hear me?
Jacob, would you mind trying
Jacob?
to say something?
Hazur, I can hear you.
Oh, okay.
I can hear him.
Oh, okay. So I can hear Jacob as well.
Otherwise, we just talk to each other.
Yeah, we two can talk to each other. Yeah. So how are you doing?
धेरै राम्रो छ. All good.
Very राम्रो छ. हजुर.
The speakers are not working, so when they speak, we cannot hear them.
अहिले तपाईँ कहाँ हुनुहुन्छ?
अहिले म इटालीमा छु.
इटालीमा ए
हजुर, तर मईमा काठमाडौँमा आउँछु. हजुर.
ए हेर्नु पर्छ ल.
वो यो वर्कशप छ, यो रिएक्ट वर्कशप इटिएच सिरिकको सँग.
ए
हजुर.
मलाई थाहा मेमा भन्नुभयो है, मार्च अप्रिल मे.
Okay.
हजुर.
अहिले आवाज आयो?
उता
Can you hear us?
Could we get it just a little bit louder, please?
होइन.
ए छैन.
अहिले हाम्रो यो मिटिङ नेपालीमा गर्छौँ.
हजुर. मलाई थाहा थिएन तपाईले यति राम्रो नेपाली बोल्नु हुँदो रहेछ.
धेरै राम्रो छैन, म कोसिस गर्छु, तर आज भोलि मात्र यो इङ्ग्लिसमा बोल्छु.
ए मेमा आउँदा भेट्न मिल्छ होला नि?
हजुर.
हजुर है.
हजुर. म इमेल लेख्छु. हजुर. म 4 मईमा आउँछु र 11 मई 12 मईसम्म म काठमाडौँमा आउँछु. हजुर. यो ट्रेनिङ वर्कशप इजी मोडमा छ.
इसी मोडमा ए ल. त्यो के सबैलाई बोलाउनु
Okay, sorry to interrupt. But we've got the sound working now. So, Daraj, I'll let you proceed, please. Thanks.
Yeah. So I was thanking both James and Joe for including me, and I was saying that it's great to be with among all the great scientists and glaciologists. So are we having my slides presented, or am I going to share myself? No.
Daraj, share your slides. Yes.
But I'm okay. Now I can see. Okay. Is my slide visible now?
Yes, thanks.
Good. Okay, thank you. So when you are having their, World Glacier Day and World Water Day celebrated in 2 days, we are having here 1 week celebrations starting from 17 March and till the day after tomorrow on the 23rd March. We celebrate it here as an Glacier Water and Weather Week. So my topic that is provided as improving water resource estimation and risk assessment in the Himalayas. So within this 10-minute talk, I'm going to focus on 2 major topics. One is how climate change is altering glacier melt and changing the snow dynamics, increasing the risk of disasters. And the second one is on accurate data and improved hydrological models that are essential for risk reduction and water resource management. Most of the contents that has already been shared by our previous previous speakers, so it's going to be faster for me. I am sharing 2 recent floods, one in India and one in Nepal, which is caused by some changes in cryosphere in high mountains. So the Himalayas, which is third pole, is considered as a freshwater resource, but there are changes in precipitation. Like Francis has said, there are changes in precipitation phase, which is the key drivers of cryospheric changes in the Himalayas, which leads to the reduced water availability and also impacting the winter crops in particular. And whole day today, we were also talking about the glacier lake outburst flood, kind of, events increasing in recently and impacting the infrastructure and people, droughts and other floods. And there is one major thing that we were discussing is uncertainty in a seasonal water supply, especially during the dry seasons, which is impacting the energy hydropower generation. So there are some challenges, water resource estimation with that, mainly related with limited data availability, especially in the extreme terrain in high altitudes. And previous presentation, we talked about precipitation, but there is a very limited and low quality solid precipitation measurements. And we still don't know well, how the gradient, precipitation gradient is in the high mountains in the Himalayas. And there is still the uncertainties in modeling, particularly participating snow and ice melt contributions. And definitely there is a lack of risk assessment, seasonal variability, and extreme events that needs better forecasting tools. And the another important part is the permafrost thawing, which needs to be addressed for the risk reduction. So I'd like to start with some community assessment we are continuously doing with in the western part of Nepal. This is when we talk with the local communities, we understand what is happening in the local climate. Particularly, they were sharing how the precipitation phase is changing from snow to rain. They in 2009 and 10, when we surveyed for the impact of climate change, they shared with us that they used to have a lot of snow, like they still measure in feet, so 2 to 3 feet in the past, and not much, like 1-2 feet that time. But last year when we were there, they started saying in 2023 and 2022 they didn't even have any snow events. So that is what happening, and definitely there are they observed that dry seasons are getting drier, and in a spring waters, which are the source of the water, they are not reliable now. And one of the major impacts is in the winter crops. And one important part, I'm sure Jakob remembers this, after the earthquake, one of the villages in Langtang was completely filled by debris, one whole village. So landscapes are changing. Not only the glaciers are changing, but there are some landscapes are changing. So calibrated models may not work in such situations, and therefore we need to have physically based model, especially in these high mountain regions, to work in the future scenarios. So this is one of the example, how the landscapes are changing. And one another challenge is that the Himalayas is facing is very sparse distribution of meteorological stations in high mountain areas, and left this size part of Nepal, we do not have many observation in the areas where we have snow and ice cover or glaciers. Similarly, this is the station distribution from Bhutan. So most of the glaciers are in the northern part of the Bhutan, but the station distribution is very sparse in this condition as well. And one of the approaches for filling this gap, we are discussing that maybe citizen science approach, and also including monasteries as a location for our stations could be a solution for Nepal and Bhutan. And we try to see whether their distribution is in the high mountains, and we found yes. And particularly, we are choosing monasteries because of three major reasons. One is they are private property, so owned by monasteries. So there is no hassle for taking permission from the national park because if we need to put stations. And the second thing is they are secured, and the chances of vandalism is very low in the case of if we use their location. And the third one is there is a high chances that those areas or the monasteries are with some one deer throughout the year, so that they can take care of the stations and do the measurements. And also the final one is that they have a very good tradition of disseminating knowledge or from lamas to monks. So that is what we thought this could be one of the approaches. And another one is advances on snow and ice monitoring, especially new technology like we discussed earlier. Satellite data are there, some new very high accurate instruments, something like ADCP, and some of the approaches. One of the approaches that we can use, and we started doing that with UNESCO, is labor project that engages local communities for data collection with low-cost census. And with that, I kept on difficult on pronouncing her name. Francisa mentioned about reanalysis data. When there are data gaps, then we can have reanalysis product use, but definitely it needs to be bias corrected with the available observed data. So this is one of the examples from Langtang station, how we use the ground-based observation to bias correct reanalysis data. And the another important part is the modeling, where we need to have a glacier and snow melt in hydrological models. And with this, we are considering cold region hydrological model in some of the areas in the our region in South Asia and China. So this is one of the projects we are implementing. We launched the project last month, and this is for especially understanding and using model to see the changes in precipitation, how it is shifting temporarily and spatially. Along with, we are also having community based assessment and interaction, not only for collecting data, but also for making them aware and implementing the advocacy or policy impacts in that. And these are the collaborating countries I have listed. It is funded by Asia Pacific Network for Global Change Research. And one of the major component of this project is also to understand change in precipitation phase using CRE model. And these are the sites selected for Nepal, Karnali River Basin in a western part, and Mustang in another basin, and Langtang, and as well as Everest Khumbu River Basin. And a few examples, few recent results that we have got from applying CREAM model in one of the glaciers in Langtang. So we applied CREAM, Langsisa Glacier, and partitioned, how different components are contributing to the basin flow. And this is one of the student supervised by John and myself, and recently defended his master. And he applied the CREAM model to see the impacts of black carbon on snow water equivalent, snow melt, fern melt, as well as glacier melt. And this is one example that I'm showing you how the impact of black carbon is a model falsification with and without black carbon, and see the impacts. And similarly, in one of the other examples that we applied CREAM for understanding how the change in landscape or glacier in the Langtang River Basin. So we falsified the model, and we try to see what will happen if there won't be any glacier in the future. And I'm happy that the presentation, first presentation by Brian, clearly, the cartoon was so clear to see these kind of impacts. But here we use the prim and falsified and see the impacts of not having glacier in the future. So in summary, I'm trying to summarize my presentation that we need to have a physically based models with proper data and for snowmelt and ice melt segregated, and we need to see the changes in climate and cryosphere together and how they influence the mountain hydrology. And in the Himalayas, there is a very big concern of black carbon, and it is also vital. It is playing vital role in fast melting of snow, fern, and ice reserves. And as we know that due to the data gap, reanalysis data could be one alternative, but they are still uncertain, but they need to be bias corrected before using it as a forcing data for any model. And finally, the collaboration among the researchers, policymakers, and communities are needed for the science, because we understand that science is for the society and for the nature. And I'd like to end my presentation with our initiatives in Nepal, particularly while celebrating World Water Day and World Meteorological Day. We started in 2009. John was there. And in 2025, after 16 years, John was back, and he made his presentation on 27th of February at Ishimode. And it was a part of International Year of Glacier Preservation as also the start of this week. Thank you for the opportunity to share some of my work over here. Thank you.
Okay, that was wonderful. Thank you so much, Jiraj. Okay, so now I'm actually going to turn the floor to Dr. James McPhee here, who's going to moderate our panel discussion. Dr. McPhee is a professor in the Department of Civil Engineering at the University of Chile. He's interested in hydrological processes of high mountain areas, including snow hydrology, glaciohydrology, and water resource systems. He's the lead of the Research and Monitoring Task Force for the International Year of Glacier Preservation. And to you.
My fingers are working. Thank you, Zoe. We've heard very nice presentations, and we have a stellar group of panelists now to follow. I would like to introduce them. Dr. Inés Dusayant is a research officer at the World Glacier Monitoring Service at the Department of Geography of the University of Zurich. Her research specializes in glacier mass change observation from in situ and remote sensing, contributing to the global understanding of recent glacier changes and their impact on hydrological systems. We also have Dr. Jesus Revuelto, who has a degree in physics from the University of Zaragoza and a PhD in climate sciences from the University of Vigo in Spain. He's currently a senior scientist at the Pyrenean Institute of Ecology in Spain, and his main line of research is the observation and understanding of the evolution of snowpack and glaciers in mountain areas. Here with us today also is Dr. John Pomeroy, who's a UNESCO Chair in Mountain Water Sustainability and a distinguished professor and the Director of Global Water Futures Program, and a Chair of the International Network of Alpine Research Catchment Hydrology, as well as the Co-Chair of the UN Advisory Board for International Year of Glacier Preservation. He specializes in snow and ice hydrology. And finally, joining us remotely is Dr. Jakob Steiner, who has 20 years of experience working on the cryosphere in Greenland and high mountain Asia, including numerous field expeditions, as well as working with policymakers based out of Nepal and Pakistan. He focuses on risk dimensions of changing mountain landscapes and our data needs to address them. He's a postdoctoral scholar at the University of Graz in Austria and a fellow at the Himalayan University Consortium in Nepal. So thank you all for joining us. I will pose questions to each one of you based on your past experience and research focus. Of course, you're free to answer those questions or to talk about anything else that you feel like, including your reactions to the talks that we've seen so far. So I would like to start with Ines and ask, what do people misunderstand, or what do you wish people were more aware of in terms of the differences between remote sensing and in situ techniques for hydrological and or glaciological applications? Ines.
Thank you, James. Thank you for this question. It's a pleasure to be invited to this panel and be surrounded by a lot of specialists in the observational field. So many people have already talked about glacier change observations, which is what I do and what I have been doing for the last 5 years in the World Glacier Monitoring Service. And the message that I would like to show of my digging into the data of glacier changes, of the different ways of how we measured glacier changes, which is one by remote sensing and one by in situ measurements, would be that they are not mutually exclusive, but they complement each other. And so basically, satellite observations give us a very good idea of what's happening on glaciers over long time periods, so the long-term trends of glacier changes. But because of issues of density conversion, because they measure surface, so we compare surfaces, because of the issues of this density conversion of snow and ice into water, we cannot really get the mass balance over lower periods of time, like annually, for example. But they are very accurate for long-term trends. On the other side, in situ measurements, they sometimes have some issues on the long-term trends because of measuring uncertainties, but they are very good at representing the annual variability and even the seasonal variability of glacier mass changes. So what we have been doing in the World Glacier Monitoring Service is to fuse these two data sets to get an observational data set that is showing both accurate long-term trends and mostly accurate annual glacier changes. And why here I say mostly accurate annual glacier changes, and this is probably what we don't know, and some people don't know about the glacier observations, which is that remote sensing allows us to have a very good spatial coverage of the world, but with in situ measurements, which is the one that are giving us the annual variability, the measurements are very scarce. And a good point here is that on regions that are well observed, so that have a good representation of glacier changes on in situ measurements like the Alps, the techniques to fuse these two observations are very well established and validated, so they work very well. But the main issue is the regions that are not well represented. So, in fact, we have knowledge and we have good data to have good observations of glacier changes, except going to lower annual resolutions in regions that are not well monitored. So my message here would be both observation techniques are important, remote sensing and in situ measurements, but there's a huge need to improve the regional and sub-regional representativity of the glaciological measurements in specific regions, and both are important. There is a concern of some people thinking that satellites are going to how do you say, to be able to show all the glacier changes at annual and even lower time resolutions, but in fact, we need in situ measurements, and it's not only because I am a romantic scientist that I like in situ measurements. They are really very valuable, and we need to continue the monitoring and sustain them in time and have a better spatial representation so that we can use these observations to really predict what's going to happen in the future.
Thank you very much, Ines. I will continue with Jakov. Can you hear me, Jakov?
Yeah. Yes, absolutely.
So a question for you would be, where do we stand on managing the data that is collected in regions with a relatively less developed infrastructure, like, for instance, high mountain Asia, where you have experience? How can we make sure that this data that is collected there is integrated effectively into our global understanding of cryospheric change?
Thank you very much, James, for having me, and Zoe, and I'm very sorry that I cannot be with you in Paris today. I want to give you the view from high mountain Asia, from a couple of sites we have heard about today already. The last couple of weeks I spent consolidating different cryosphere data, all the way from Tajikistan, Afghanistan to Bhutan, that has been collected over many years. And you know that has been collected by governments, by different research agencies. And the good news is there is actually quite a lot of data around, and I think we made a lot of progress in monitoring more in this region where we often talking about the lack of data. The bad news is that this data is often hardly accessible at all, and if it is accessible, it's in a state of documentation that makes it very, very hard to do anything with it, right? So to give you an example, today, for example, so I had a discussion with two different research groups from Europe who are, unbeknownst to each other, going to this month start new instrumentations, excellent instrumentations in Nepal of the cryosphere, in a catchment that already has a lot of data. But the data that we already have is spread across different hard drives on the globe. And sometimes I wake up at night not with climate anxiety, but with data mass anxiety, because we have collected so much already, and I don't know what we're going to do with the new data that's going to come in. So I think what we'll need to talk about is that how do we deal with the data that is coming in from the different monitoring initiatives. And for that, the first step, in my view, is to try to understand what is the lack of incentive to do a better job in documenting data, right? So this means providing opportunities for all those people who are doing tremendous work in these different countries to collect data, to actually also store this properly. Not just say, please share the data, but first, make sure that it's in a safe place and that it's properly documented. And that's not just money. That's being able to join initiatives that are global, like INARCH, which is a fantastic initiative on the global scale, right? And of course, WGMS, but I'm talking about cryosphere variables beyond mass loss. And the second one is developing frameworks on how we actually have to store this data. And there are smart solutions, technological solutions to do this by now in a way that it's not just Excel sheets that then disappears on different hard drives. And I think the opportunity here is that, teaching in the region, in Pakistan, in Nepal, I see there is a lot of new early career scientists coming up who are excellent data managers, excellent data scientists, who would be really, really motivated, who may not be super excited to go on a glacier, but who are really motivated to find new technological solutions to deal with all this data, right? They're very smart in doing that, much better than I am able to do it. And they would like to be involved in these initiatives, and they would like to be given opportunities to work on this technological side of data management. So, but this needs money as well. Yes, monitoring is exciting. I'm also a romantic scientist like Ines. I have spent all my research career in Greenland and high mountain Asia running around on glaciers, and I keep enjoying doing that. But I think we also must not forget that managing all this data also needs financial investments, and it needs patience and time to build trust between the different stakeholders, and we shouldn't forget that. Otherwise, we lose all the initiative, all the money, and all the risk we took to collect that data if we don't actually, if you don't cherish this. This is largely about in situ data. If you don't cherish what we have invested and don't make sure that it's properly curated. And I really hope that in future we do a better job in this regard.
Thank you very much. It's a very provocative thought as well. I would like to move on to Jesus and ask you to expand on the idea of what do you think that our understanding of cryospheric change in the Pyrenees in particular, moving to that region of the world, is it sufficient to address the future impacts? And what could the community do to improve the understanding of that system in the near future?
Okay, so thank you very much for the opportunity of being here and sharing our work in the Pyrenees. Well, the Pyrenees are a small mountain range when it's compared to other mountain ranges, but are undergoing profound changes due to the rising in temperatures. And we know that several processes related with the cryosphere are happening. For example, the glaciers in the Pyrenees are vanishing. In a few years, we will not have glaciers and we will become a free ice or a glacier free mountain range. So this is quite important. Since the Little Ice Age, we have lost about the 90% of the surface, and also the thickness, since we have more accurate observations with close range techniques. We know that we have lost about 15 to 20 meters of ice thickness, and this is in a really shallow ice thickness. So for sure, in the near future, they will disappear. Also, the snowfall is changing, and we will not have quite long snow season as we had before, and for sure we will have a higher uncertainty. We will have years with a remarkable snow presence, but more frequently we will have years with less snow. And an interesting point also is the permafrost. We know that in some areas of the Pyrenees there is permafrost, despite we do not know exactly its distribution. We know that there is permafrost, and also it's destabilizing. So this will affect to hikers and the access to the summits in the Pyrenees. So this is also really important. So what can we do to address and to improve our understanding? Well, we have climate models that are advancing the future of temperature rising and other meteorological variables, but we need I think that we need higher spatial resolution simulations in those really small glaciers. Also, as my colleagues Francesca, Jacob, they have mentioned that we need more data. We have to improve the management of those data, and especially in high elevation areas. We know temperatures in the lower areas of the valleys, how were those temperatures some years ago, but we do not know how those temperatures were in the higher summits. So we need to expand this monitoring, and we need also to have more long-term initiatives to observe the evolution. And also in the Pyrenees, this mountain range between Spain and France, we need to expand cross-border cooperation between researchers to share the data, and also with policymakers to propose adaptation and mitigation policies, and to advance the situation. For example, if glaciers disappear, this will affect our landscape. So we have to advance this future situation. And one relevant point for the Pyrenees, despite they will be without glaciers and the cryosphere is changing quite rapidly there, is that they are advancing what will happen in about 10 years or 2 or 3 decades, what will happen in other mountain ranges. Because, for example, the Alps are close to the Pyrenees, but they are more cold, they are higher, and the situations that we have now in the Pyrenees will happen in the near future to other mountain ranges. So this is a really nice, well, let's say, laboratory for all researchers to say what can happen in other areas of the world. So this is an important point to study and to understand the evolution of the cryosphere in this mountain range.
Thank you, Jesus. And last, we closed the panel with Dr. John Pomeroy, and with the question of what field. We've heard about field data, we've heard about modeling exercises and the importance of research catchments. And in your opinion, given the advances and given the progress that has been made, what do you think is the field data that is needed still to improve mountain cryospheric change predictions? And at what spatial resolution, what level of detail and process understanding would we need to achieve for proper mountain hydrological prediction models?
Thank you, James, for the question and for the chance to participate on the panel. In terms of the field data, it's something I thought about very much, and all of our models fail or succeed on the quality of the precipitation data that's available for them, particularly the measurement of snow, which is very difficult because of the relatively low terminal fall velocity of snowflakes compared to raindrops. And so our collection gauges are not very good when they look like this. They need windshields, as Francesca mentioned earlier. She's completely right. But our windshields are also not very good. A very good windshield is the DFIR reference, the WMO, which is incredibly difficult to build, particularly in a high elevation area. Where they exist, they're the gold standard. But otherwise, we have to put up with gauge corrections for altar shields with a fantastic scatter in them. And we know there's a temperature dependency because it depends upon the fall velocity of the particles and the characteristics of turbulence around them. So this is still not very good. But we need them at high elevations nevertheless, and the higher the elevation we put them, the windier and the less suitable it is to have such a gauge. But we still have to do it. And we just, with my PhD student, Andre Bertoncini, we just published a paper in the Canadian Rockies on the uncertainty of mountain precipitation. And if you typical gauge uncertainty, you look at a map, you look at the points on the map, and it looks, oh, pretty good. There's lots of points on the map, particularly if you make the points big. But when you look at elevation, in Canada, we put them in the valley bottoms. Why did we do that? Well, one is our Federal Weather Service was part of the Department of Transport, so they put them at airports. And then they put them in communities. That's great, but they're all in the valley bottom. And then why not high in the mountaintops? Well, there's no roads up there. You have to climb to go get to these things. And so there aren't very many. But the impact of just putting a few gauges up high, particularly in a transect where you can work out the lapse rate of precipitation with elevation, is incredibly high impact on reducing the uncertainty in that precip over the whole region. And so it's worth doing it, even though it's very, very hard and very difficult and still highly uncertain. One other thing I'll say, what are we missing from the ground very often is albedo, particularly now that we have increasing dust, soot, and pollution impacts on glacier and snow surfaces and increasing algae blooms. And our models are not very good at handling these really anthropogenic inputs to albedo on these surfaces. We're measuring glacier albedos of 0.15. It's darker than a field, in a farmer's field out in the prairies. So these are out of the textbook values, and we found a substantial improvement if we could assimilate either measurements on the ground or a high-resolution satellite information into the hydrological models. That's one area we found where we can improve them. And then we'll go into modeling. Before I came here, I was looking at an old report I found in my office that I hadn't seen for a long time. In fact, I hadn't seen it for 40 years. It's the original blowing snow model and a series of 68 equations working out the transport of snow as a two-phase flow through saltation, suspension, and then sublimation of the particles in a turbulent atmosphere. And so 40 years ago, we wrote up the first one. And there are others that are out there now. There's a number of these. And so they're all difficult. Two-phase flow is not simple. Bagnall said it was a new phase of matter that he called fluxon, but that's Bagnall. The thing is that we've been able to show, and many have shown time and time again, the absolute importance of wind redistribution of snow in alpine environments, and as well as the subsequent avalanching of the snow and redistribution by gravity when the cornices start to collapse and go down. So many pocket glaciers only exist because of snow blowing in to these coulees on the coombs on the north face where the accumulation can occur. And the late-lying snowpacks that we rely upon for base flow in the summertime are from snowdrifts or avalanche deposits of drifted snow that further come on. And the sublimation losses during wind transport can be very large, on the order of 30% in the mountains. So we need physically complete as well as physically based cryospheric hydrological models. And we need to be including this process. We've had the equations out there and the models out there for 4 decades now. And I don't think it's excusable anymore that they be excluded. The recent work by Chris Marsh has shown that the importance of these scale up, and they also persist over time. So they're emergent processes. And work did with Michael Shermer in the Rockies showed that the redistribution of snow had a 7 times greater influence than variation in melt rates in controlling the snowmelt in the midsummer on these slopes. So we need to get that snow mass and the SWE right, and that means we need to include redistribution as well as accurate snow measurements. We have to account for sublimation losses, and then we need to still account for the melt rate, but important. And I'll say one last thing. So this morning, I got a request to review a paper from a famous, well-known international journal to review a series of temperature index models. I told them to go stuff it. It's time to see the end of non-physical based temperature index modeling. Nobody submits Lamarckian evolution, and we accept Darwin now finally. But the energy balance has been perfectly capable of being calculated for decades now, given our models. We know that there are spurious correlations behind the temperature index. It's really accumulation of time versus time that causes a false correlation. When we accumulate these things, we fool ourselves in doing so, and it's a false predictability, and it's anti-scientific. And it's time, I think, now to take a very strong stand, and these papers should not be anywhere in any reputable scientific literature. So that's my happy message for the end. Thank you.
On that happy note, I would like to offer the floor for the audience, maybe people connected online, to ask questions, to offer their perspectives and opinions, and of course, members of the panel and the speakers. We have time. We have 1, 2, please.
Thank you very much. I just want to reflect to what Professor Pomeroy just said. I understand you saying that we should stop temperature index-based modeling approach and then go for energy balance-based modeling, but data is an issue. So how do we deal with data in high Himalayan area, especially in Central Asian region, where we do modeling? We have tried to do modeling with energy-based modeling approach, but then we don't have wind speed data, we don't have radiation data. We are very much happy if we can find one or the other point where we have temperature and precipitation information. So, yeah, I want to hear your opinion on this.
Yeah, yes, no, it's a problem we have in Canada as well. So first thing, it's important to get the precipitation right, as we mentioned, I think we agree. And then the second, for the data requirements for energy balance approaches, there are ways to estimate the radiation from the daily temperature fluctuation and humidity in the atmosphere. Dheeraj Pradanaga worked on this as part of his PhD. So there are techniques to do this and synthesize this when you don't have that data available. And we find they're as good, sometimes a little better than reanalysis data for radiation. But then there are also the reanalysis models. The ERA5 is not too bad for radiation and for wind, and with a few stations to do a regional bias correction can be made much better, as an example. So the others, the temperature index goes back to when there were thermometers in Stevenson screens and people shook them every day for the max min and things like that. So, but now we tend to have, if we have temperature, we probably also have humidity, and it's not hard to add wind speed. And even a incoming solar radiation measurement is about the same cost as the temperature humidity device once you have a data logger. So I think it's possible, and then that with the addition of reanalysis data to force these things means that we can do it in a distributed fashion.
Thank you, Thomas, and then we go to Jakob.
Yeah, so well, first of all, thank you everyone for these lovely presentations and the panel. So, I mean, John's already kind of pointed towards, the real need for precipitation. So that kind of already covers my first question. But what I'm most interested in the sort of opinion and the consensus on how do we best push for these increased high elevation observations, specifically for precipitation or other meteorological variables? And how do we best sort of capacity build to both install and maintain sort of long-term observations? So not just from INARCH and these amazing setups that we have, but also in these other many, underrepresented places. So how do we best, do that? Do we go for sort of big funded projects which can just install, millions and millions of things, or do we try to build, through local agencies, communities, and such? Just interested for any any panel opinion on this. Thanks.
Does anyone like to comment on that or to address? Yes. Can you? Yeah.
So we've talked a lot about observations and how precipitation is important, and we have done a lot of precipitation observations, but one of the things that we haven't really mentioned yet, I think explicitly at least, is the maintenance of the quality of those observations. So in all our precipitation measurement networks, we recalibrate everything in place 2 to 3 times a year. So we can be assured that we have science-grade measurements. Now, we don't need science-grade measurements, right? Within 5% of accuracy of calibration everywhere, because we can make corrections, but it's not a small endeavor to do that kind of maintenance, right? And so I just wanted to recognize the fact that in order to maintain these kinds of networks, it's really hard. But it's really critically, critically important. So on the, what was, I think I really wanted to make this point. So, and the other thing is in terms of this idea of Earth system science, right? We have been talking a lot about cryosphere and hydrology, and I think really what's different about this time is that we're ready to do Earth system science. And so we had the panels in the morning with sea ice experts and climate experts and so on. And I think that opportunity is really a huge opportunity, right? Because it allows us to put all of these parts together, and glaciers with hydrology and all of these things. And so I think as we move forward, yes, the focus on the physically based, and I like what John said about physical completeness. I love that. And but it's really also about the integration, so we can actually look at these systems in a more complete way. So,
Thank you, Anna. We move now to Jakov. You had your hand up.
Yeah, I wanted to actually go back to one of the questions that were asked by one of the speakers. Francesca was asking about, and I think it's a very important question, the representativeness of catchments, right? How do we choose where we monitor next? And this is very important, especially in regions where still new monitoring is popping up, like in high mountain Asia. So I think it would be very helpful if we had a discussion on this, if there were some guidelines. And I would also like to think about doing this more with communities, because in the catchments that we work in high mountain Asia, these are often populated, right? We do have people living there. And what we already see in some places is what social scientists refer to as research fatigue, right? This is a common term in Antarctic, for example. Too many scientists coming to the same valley again and again, and never only coming with questions and never coming with solutions, and in an increasingly politically polarized atmosphere that also exists in high mountain Asia, this becomes problematic. So it would be, we are challenging the people that live in these catchments where we work in with more and more plastic and metal that we put there, and they don't understand why we are doing this. So I think, from the question that Francesca posed, it would be something to think about in future, perhaps to talk about this in a way that future scientists, early career scientists who are building their own research catchments have some experience to build on to choose their locations, apart from the fact that, like Francesca also insinuated, logistics and accessibility is the one obvious one that I also subscribe to. Thanks.
Yeah. Thank you, Jakob. Please, Sridhar.
Yeah, I just,
Well, oh, sorry.
Oh, there is somebody talking? Or?
Oh, I thought that you're asking me to.
Oh, sorry, Dheeraj. here in the room, and maybe then if you want to add an idea. Yes, please, Dr. Maki.
Yeah, I'm Sridhar Maske, originally from Nepal, but living in Netherlands for many years, IIT Delft. One question I wanted to ask about, actually, with a lot of people experiencing monitoring and modeling, where we are in terms of the accuracy of modeling and sophisticated, etc. But that, I think the John summarized that in the end very strongly. So I do not ask that question, but that reminds me also my experience. I'm more from hydrological modeling background, not the glaciologist per se, but when you deal with a catchment model, if there are glaciers and snow, so we have to deal with it. So that's my experience in snow glaciers. And a few years back, I was in one of the snow conference in Finse, in Netherlands, Norway. And there I really feel the importance of wind drift and snow transport through wind. So that's really important component. And next to I would add, when we talk about physically based model, is yes, the energy balance is definitely the key, but there is also, we should not forget the vertical physical modeling, because when you have a very large depth, the density varies enormously, and particularly when it becomes older, the density variation is large. So if we do not do this vertical differentiation, linking to density difference, we will also add a lot of uncertainty to our calculation. So I think the wind is a super important component, and also should not forget the vertical dimension.
Okay, thank you. We are running a little short on time, but we have Francesca here. You wanted to add some? Yeah, we have time for maybe two more, you and then Dheeraj probably, and then we can wrap up.
Yes, I'll be very quick. So I want to make two comments. The first in response to what Jakob said, which was in response to what I said. I think, to be very practical, this issue of representativeness and where we put the next experimental site, somebody gets a big project and decides, okay, I go back to Langtang or I go somewhere else, should be really part of this decade of cryospheric action. I would really welcome a working group that says, hey, which are the catchments where there are a number of instruments and standard observations, and even provide a database. I mean, it could really build on INARCH. I think INARCH was a great thing, and we could put some more focus on cryospheric so that we don't reinvent the wheel every time. And then, as Jakob said, these measurements disappear, right? And we write the next big grant, we go there for 4 or 5 years, people are very tired of seeing us, we put all the rubbish there, and then we start over and over, and this pops. And I think we could build a working group for this, right? They start from, yes, building a database of where they are and think where could be the next one. And then I want to say something, I think nobody replied to Tom. Tom, I think your question was too difficult, obviously. So I try a bold answer, which I think we should go big and really say, hey, precipitation is this big unknown, is recognized across communities, isn't it, from glaciers to hydrology. So I think there should be some large funding, and this could also be part of this decade of cryospheric action, right? I mean, Walter got his ERC on this, but this is not enough, I feel. I mean, he's going to focus on a few catchments again, and I think it has to be really global. And I think I welcome that we put this as one of the action items for this decade of cryospheric action. I think we need to do something very practical out of it. Otherwise, we are all here, and then everybody goes back, and what are the outcomes?
Yeah.
So I would welcome those two initiatives, practical initiatives.
Thank you very much. Yeah, sure.
Could I just say something quickly about representative catchments?
Yes.
Back in the International Hydrological Decade, 60 years ago, they went for the concept of experimental and representative catchments because they were going to regionalize these catchments statistically over, and it failed. There were hundreds, thousands of them set up around the world, and then rapidly all shut down, too expensive to do it. What they found was every catchment's different. But if the one development in that period, though, out of the Soviet Union, is that you have good research catchments where you can regionalize certain parameters in physically based models on, then you can scale from a small basin up to the Lena River or something like that. That's a very useful concept. And so I think a modern version of a representative basin in terms of a basin that could be scaled up to a river basin in terms of its understanding, process understanding, and model verification understanding, this could be useful.
Thank you. I would like to give the last intervention to Dheeraj from Nepal, and then we will wrap it up.
Thank you. Thank you, James. In fact, I wanted to re-emphasize on community participation for our research or any act that we do for science, particularly when Dr. Sridhar Maske, I saw him sitting next to John. So I think a couple of months before, we were in downstream, one of the river downstream, and interacted with the community, and we found out very interesting observation from the community. Those were shared to us. Sridhar and I were there for a project, classic project. What I wanted to emphasize on one thing is that when we were there before that, we were trying to measure major river systems in Nepal using GNSS and ADCP. At that time, due to the restriction from national park, we were not allowed to do measurement in both sides of the bifurcation from the one of the major river system in Karnali River Basin. And we realized that the observation from or the perception that the community shared is very important, that sometimes we miss. So this is what I really want to re-emphasize, and I'm sure I don't want to keep you longer. Maybe you can talk more with Dr. Sridhar Maske when he's there about the importance of working with the community. Thank you. Thank you for the time given to me.
Thank you. Thank you, Dheeraj. Okay, so I won't really try to summarize what we've said because I will make a fool of myself. But I think this has been a very strong session. I'm really happy that we had it. There was one question in the online forum that asked about the role of National Institute for Statistics on this whole enterprise. I think it's a very good question. It depends, of course, on their local mandates and so on. But I do want to say that for reasons in life, I had the opportunity to discuss about data with librarians. And you would be surprised, and I would strongly encourage that you go to talk to your local librarian in your university and your institute, because you will find yourself that surprised in that they see themselves as a discipline with a mandate as well to manage data, to manage information, and adding a librarian a few hours on your next proposal could actually pay off quite well in terms of gathering your data and managing and keeping it for the future. Having said that, I also would like to close by acknowledging this session was a merged session, as you probably suspect, and the original proponents of the different sessions that were merged include Dr. Nazimul Islam at University of Birmingham, and of course Dr. Ignacio López Moreno, who proposed this session on behalf of the International Network of Alpine Research Catchment Hydrology, INARCH, and Mrs. Zoe Johnson and myself as co-leads of Task Force 3 of the International Year of Glacier Preservation. And so I'm very happy that we were able to have this session, and this is just the closing and the invitation to stay tuned and stay engaged, because we have a full year to go and 10 years to go for the decade of action for cryospheric sciences. And I think the opportunities that have been appearing and the opportunities that were hinted at in this fantastic session with such strong presentations are very exciting and should have all of us quite excited about the 10 years to come. So with that, just one round of applause final for everybody. Also, thanks for technical support and everything that you've done for us. And now we go to, let's go have a drink.
Thank you. Bye-bye. Kami bermeeting Kathmandu.